Okay, let's move on. Let me briefly review what we discussed in the last class. So we focused a lot on symmetry elements that include translational symmetry, and we have learned that, well, we have the glide planes, and we have overall 5 of them, A, B, C, N, and D glide planes, and we have screw axes, which can have either 2-fold, 3-fold, 4-fold, or 6-fold symmetry. So that expands the crystal classes or point groups, of which there are 32, to overall 230 space groups. So any crystal that appears in nature must crystallize in one of these 230 space groups. So as there are a limited, as there is a limited number of point groups, there's also a limited number of space groups because of the limited number of symmetry elements that there can be. So space groups are very important, and they're all listed in a very important book for solid state chemistry, which is the International Tables for Crystallography. And I would like to give you a brief overview over what you can find in these tables. So all the space groups are listed there, and each of them have a number. So they're numbered from 1 to 230. So for instance, this one here, which is called P21 over C, is the space group number 14. So you see here the 2 pages in the international tables for the particular space group. So I will not discuss all aspects of the information that you can find here, but only the most important ones. So let us more closely look at this part here. Okay. So this here is the name of the space group in the Hamann-Morgeux formalism. So this is listed as P21/C, which is read as P21 over C. So what does that mean? That means that our space group is associated with a primitive unit cell, and in one of the 3 directions we have symmetry elements. In particular, we have a 2-1 screw axis and a C glide plane which stands perpendicular to this screw axis. So this formalism here, this name here, is actually a short version of this name here. So this is the full version of the space group. And then the space group symbol reads P1, 2-1 over C1. So we see that we have some additional information here. You see here these 2 numbers 1. Okay. And that means that, well, we have no symmetry element in the A direction. We have the 2-1 screw axis in B direction, and the C glide plane stands perpendicular to the B direction. And in C direction, again, we do not have a symmetry element present. So you see here the corresponding space group symbol in the Schoenflies formalism, and then it runs C5 to H. However, in crystallography, we use far more commonly the Hamann-Morgeux formalism rather than the Schoenflies formalism. All right, so you see here 2 other denotations. So this one here is the point group associated with the space group, and it's 2 over m. So how can we understand this? Well, the point group derives from the space group when we take away all the symmetry elements that contain a translation. Okay? So now the 2, 1 contains translation, and the C glide plane contains translation. So if we take out the translation from the 2, 1 screw axis, then the 2, 1 screw axis just becomes a twofold axis. And when we take out the translation from the symmetry element C, then the C glide plane becomes a regular mirror plane. Okay, hence the point group symbol 2 over m in the Hermann-Mauger formalism. So you see here the Bravais lattice associated with the unit cell. So in this space group, we have a monoclinic unit cell associated with it, which is primitive necessarily. So more precisely, we actually talk about the crystal system when we talk about a monoclinic unit cell, not the Bravais lattice. Just Bravais lattice is associated with a monoclinic crystal system, to be precise. All right, so what else is important? So let us look next at this part here in the international tables. So you see here the unit cell in different projections. Okay, so here you see actually the, well, direction along the B lattice parameter. Okay, so here we go in A direction, here we go into C direction, and perpendicular to that there is the B direction. So you see that the angle between the A and the C lattice parameter is the angle which is not 90 degrees. Okay, so in this unit cell here, we are looking along the C direction, and our lattice parameter A is this, and our lattice parameter B is that. And in this unit cell here, we are looking into the B direction. So we go here in C direction and here in A direction, and sorry, is that correct? So unfortunately, this stupid panel here cuts off some of my PowerPoint slide. So this is A, this is C, and then this must be B, and we are looking here actually into A direction. So that's right. Okay. Now we see here in the different unit cells the symmetry elements. So here you see actually the 2-1 screw axis. Remember the symbols, the symbol for 2-1 screw axis at the position where the 2-1 screw axis runs. So the 2-1 screw axis must run in B direction. Okay, and you see here the different positions for the overall 6 screw axes, which are part of one unit cell. Okay, so it runs along B and is shifted in a quarter along the lattice parameter C. All right. Then in addition, you see the glide plane. So this is here the glide plane. So the glide plane is perpendicular to C, and you see that it's actually elevated by a quarter of the unit cell parameter B, which is actually indicated by that 1/4 along the symbol for the glide plane. So you see here these little circles, and these little circles represent inversion centers, which are also present. Okay, of course, inversion centers are independent from direction because an inversion center is a point. It's not a plane that stands perpendicular to a direction. It's also not a screw axis which runs along a particular direction. So you see the same symmetry elements here again in this other projection. So now these dotted lines here, they represent the glide planes, okay? And you see that the dots actually point into into B direction, okay? And that is because the glide plane stands perpendicular to B. So it's actually in the AC plane. No, wait a moment, this is not correct. So C stands perpendicular to B. I cannot see the entire slide, so I have to actually press the escape button so that I'm not making mistakes. This actually is really bothersome here. So actually here now we see actually the full slide. So we actually have here the B direction and here the C direction. So the glide plane stands perpendicular to B. That is correct. Okay, so it goes actually into the A direction. It is defined by the AC plane. Correct. So you see here now the 2-1 screw axes, and we have actually 4 of them here, and you see that they are also now going into the B direction as indicated by this little arrow here. I can make this large again. And you see it's only a half arrow, which indicates that it is a 2-1 screw axis. So you see again here the inversion centers as dotted lines in addition. Okay. So last but not least, you see here the same symmetry elements in this unit cell again. You see here the the 2-1 screw axis. You see here the glide plane, okay, which again stands perpendicular to B. Okay, so it contains A, and then it contains the coordinate C, which points out of the board plane. Again, you see actually the inversion center. Here as dotted, as little dots. Okay. So last but not least, you see here a different form of the unit cell. We are now looking again in B direction. And you see actually here what the screw axis just do with an atom. So we rotate by 180 degrees. If you, for instance, put yourself on this atom here, and then you move by half of a lattice parameter in the B direction. All right. So now here you see the symmetry operations listed. So we have the identity, we have the 2-1 screw axis, we have the inversion center, and we have the glide plane. And you see here the positions of the symmetry elements within the unit cell. Okay. So for the screw axis, you can see that we have the symbol 2, and then the coordinates 0, 0, a half, 0, and that means that we basically shift by a half of the lattice parameter in B direction. Okay, and 0 y a quarter. Okay, so that means that the coordinate y here is variable. So that means that basically, well, the coordinate y in B direction is variable, producing the line. And then this quarter means that basically the 2-1 screw axis is moved by 1/4 of the lattice parameter C. Okay, it is moved a 0 fractional coordinate in the A direction. Okay, so this corresponds with this picture here. Okay, we have to go from here 1/4 into C direction. Okay, but we are not going at all into A direction. Okay. So the other 5 screw axes that you actually see in the unit cell, they're actually just produced by the other symmetry elements within the unit cell. Okay, then we have here the center for the position for the inversion center, which is just at the origin, and all the other inversion centers follow due to the symmetry of the unit cell. So last but not least, you see here the position of the glide plane, a C glide plane, and its position x a quarter z. Okay, so basically x and z are variables. Okay, that has to be so because the AC plane, the XZ plane, well, defines the plane. And then that plane is shifted by 1/4 of the lattice parameter B into B direction. Okay, you can see this. We can see this here, for instance. Okay, so we shift that lattice, so it's that glide plane here by a quarter into the B direction. Okay, you see this again here. We shift that glide plane here a quarter into B direction. Okay. All right. A few more things about the second page. So I just press escape here because I can see only part of my slide. So you see here what is called the so-called Wyckoff positions. And these Wyckoff positions indicate where the atoms can sit in the unit cell. Okay? So this position here is what is called a general position. And a general position is defined as a position where the coordinates are variable. Okay? So when the coordinates are variable, they have just the general definition of x, y, and z. So basically anywhere in the unit cell, but not on a special position which we discuss, which we will discuss in a bit. So now associated with this most general position, there are 4 others, and these 4 others are created by the symmetry elements and symmetry operations. So most easy to understand is this one. So that is x bar, y bar, z bar, and that is produced by the inversion center. So any coordinate x gets converted into minus x, any coordinate y gets converted into minus y, any coordinate z gets converted into minus z. Okay, so this one here is produced by the screw axis. Okay, so it has the general formula x bar, y plus a half, z plus a half. Okay, so as we rotate around y, the x coordinate, x becomes minus x, okay, and the y coordinate shifts by a half of the unit cell, and the z coordinate also shifts by half of a unit cell. So this last one here is produced by the glide plane. It has the denotation x, y bar plus a half, z plus a half. All right, so now in addition to these 4 general positions, we have 4 special positions. So these are these 4 here. Okay. So these are fixed positions within the unit cell. And their multiplicity is smaller because they are located on 1 or more symmetry elements. Okay. So the multiplicity is given by this number here. So for the general position, it's the highest because the position is general and all the symmetry elements act on the atom within the unit cell and produce overall 4 positions. But here, the multiplicity is only 2, meaning that the symmetry operations produce less many additional positions, create less many additional positions. So for instance, when an atom sits on the position a half, 0, a half, then the symmetry elements only create 1 additional position for the atom within the unit cell, which is a half, 0. If it sits at 0, 0, a half, you're getting another position, 0, a half, 0. If it sits on a half, 0, 0, then we get another position, a half, a half. And at 0, 0, 0, we are creating another atom at the position 0, a half. Okay. So now associated with these positions, there are general reflection conditions and special reflection conditions. They're also called systematic absences. So that means that when our substance crystallizes in the respective space group, then we cannot see all possible reflections, but only some of them. And the elimination of certain reflection follows a specific systematic pattern. Therefore, there are some of them are systematically absent. Okay, and in particular, we can have only we can only observe reflections in our X-ray diffraction pattern when for reflections that follow the Miller indices H0L, and I will explain later on exactly what Miller indices are, for L is equal to 2n. Okay, so that means that L, basically L, has to be an integer number, okay? K has to be 0, and H can be variable, okay? So for reflections of the form 0K0, K must be an integer number, H and L must be 0, and for 0, L must be an integer number, okay? So now these general reflection conditions are created due to atoms located on the general positions. So these so-called special reflection conditions are due to atoms sitting on these four special coordinates. Okay, so in particular, for these coordinates, K plus L must be 2n, and that is actually true for all the positions. Okay, so in addition to these general reflection conditions, we also have the condition that K plus L must be 2n. All right, so very briefly, I would like to talk about that part of the page here. So this part here lists so-called subgroups and supergroups. So a subgroup is a space group from which certain symmetry operation and symmetry elements are eliminated. Okay, so for instance, P121 or P21 is a subgroup of P21 over C because the C glide plane has been eliminated. P1 is a subgroup because both the screw axis as well as the C glide plane has been eliminated. P1C or PC is a subgroup because the the 2-1 screw axis has been eliminated. So now a supergroup is basically the opposite. So supergroups are groups based on the group to which other symmetry operations have been added. Okay, so you add additional symmetry elements to the two-fold 2-1 screw axis and the C glide plane, then you arrive at what is called a supergroup, and there can be a number of them, and they are being listed here. Okay, so this was a brief overview over the international tables for crystallography, and that actually now leads over to the second chapter in our course, crystal structure determination. And crystal structure determination is mostly done using a technique called X-ray diffraction. So you create an X-ray diffraction pattern from your crystal structure, and then with the help of symmetry and the help of the international tables for crystallography, you can determine the crystal structure from your X-ray diffraction pattern. Okay? So X-rays, as you know, were invented, probably know, were invented by Wilhelm Conrad Röntgen, who won a Nobel Prize for the discovery of X-rays in 2001. He is, however, not the discoverer of X-ray diffraction. He already discovered that X-rays can be absorbed by matter, and that this X-ray absorption can be used in order to see the bones of a hand. This is a famous X-ray image here. So this is actually the hand of Röntgen's wife, and you see she has a ring around her finger. Okay? So that image is not being produced because of the phenomenon of X-ray diffraction, but because of the phenomenon of X-ray absorption. So the bones absorb more X-rays than the flesh around it. So for that reason, we can actually image the bones within a hand using X-rays. Okay. However, this is not X-ray diffraction. X-ray diffraction was discovered by Max von Laue, who also received the Nobel Prize for his discovery in the year 1914. So he discovered when you actually produce X-rays related to a LED screen and bombard a crystal with it, that then the X-rays get diffracted and you get a so-called diffraction pattern. So when you diffract X-rays at a single crystal, you actually get a characteristic pattern of, well, dots on a photographic plate. And basically the pattern that you produce is characteristic for the crystal. So the pattern which is produced is a signature of the crystal structure. Okay? And the principle of crystal structure determination from X-ray diffraction is to analyze the diffraction pattern, and using certain methods, which we will discuss in more detail shortly, derive the crystal structure from the observed X-ray diffraction pattern. Okay, so how do we generate X-rays, and what is the instrument with which we determine the X-ray diffraction pattern of a single crystal? So we use an instrument called a single crystal X-ray diffractometer, which contains an X-ray tube where X-rays are being produced using a higher voltage. Okay, that high voltage is produced by a high voltage generator within our X-ray diffraction instrument. So how does an X-ray generator work? Well, it's generated in a so-called X-ray tube, which contains what is called a rotating anode. So you see actually here the electrical circuits that are present within an X-ray tube. You have actually two electrical circuits, one high voltage circuit and a low voltage circuit. So let us look at the low voltage circuit first. So in the low voltage circuit, we produce a high current that heats a filament to a very high temperature. And due to that high temperature, electrons are being ejected. Okay? Basically, the electrons that flow through that filament due to the high current collide with electrons within the filament, and these collisions can eject electrons. All right, so now these electrons are being ejected, and now these ejected electrons are accelerated in a second circuit, which contains a high voltage. Okay? And this voltage is typically in the order of tens of kilovolts. So 40 kilovolts is a typical number. So these highly accelerated electrons, they then hit an anode material. So that anode material is typically a metal. Copper is very common. Molybdenum is another very common metal. And upon that collisions, X-rays are being emitted. So that anode is typically a rotating anode because these collisions of the electrons with the anode produce a lot of heat. And for heat dissipation reasons, that anode is being rotated. So this increases the lifetime of the anode. Okay, so now how exactly are the X-rays being generated as the electrons hit the anode? So we can see this here. So the electrons themselves, they emit X-rays because the incoming electrons that are about to hit the anode are very fast. So an electron is a charged particle, and a fast-moving charged particle has to send out electromagnetic radiation, and the electromagnetic radiation wavelength depends on the speed of the electron. So these electrons have a speed distribution. So some are faster than others. So for that reason, the X-ray radiation they send out is called a continuous radiation. That means that they have a continuously variable wavelength. They have a wavelength distribution, okay, or a frequency distribution. Okay, so then our electrons hit the electrons within the atom, and they are so fast so that they can eject electrons from an inner shell of the atom, and that shell can be as low as the most inner shell, the K shell. Okay, so that produces an ejected electron, okay, in addition to the electron that has ejected the ejected electron. So both electrons have a certain velocity. So because of that, they both send out electromagnetic radiation, And the wavelength of that electromagnetic radiation again depends on the velocity. Therefore, again, these electrons send out continuous X-ray radiation. Okay? So now, however, there's a third process, and that third process now produces what is called characteristic X-rays. So now an electron from a higher shell, which has not been ejected, can actually make a transition, electron transition, to a lower shell because there's an empty slot in the lower shell because of the ejected electron. Okay, so that process is associated with a very discrete energy difference. Okay, and the energy difference between the two energy levels is associated with X-rays of a characteristic wavelength. Therefore, these wavelengths are being called characteristic X-rays. All right. So this continuous radiation is sometimes also called Bremsstrahlung because of the deceleration of the electrons, which is uncharacteristic, whereas this is the characteristic radiation because of the discrete electron transition from a more outer shell to a more inner shell. All right, so in X-ray crystallography, we usually use so-called K radiation, and that means that we use radiation which is produced from the transition of an electron from an outer shell into the K shell. Okay, so now you see here on the left side the intensity distribution of the X-rays associated with the copper anode. Okay, and you see here the intensity distribution associated with the molybdenum anode. So you see here the continuous radiation, okay, and then on top of the continuous radiation, you see the characteristic radiation. Particularly, so here the K alpha radiation and the K beta radiation, okay? So now, what do we mean by K alpha? By K alpha, we mean radiation associated from the transition of an electron from the L shell to the K shell. Okay, and by K beta, we mean the transition from an M shell to a K shell. Okay, so the energy difference between an M shell and a K shell is larger than the energy difference between an L shell and an M shell. Therefore, the K beta radiation has lower, smaller wavelength in comparison to the K alpha radiation. If you look very close, you would actually see that there are even finer lines. So actually the K alpha radiation is composed of what is called the K alpha 1 and the K alpha 2. Okay? So the K alpha 1 is actually produced from the transition of a 2p electron in the L shell to the K shell, and the K2 K alpha 2 radiation is produced from 2p electron into the K shell also, whereby these 2p electrons have a different quantum number L. Quantum number M. So, but this is only a subtle difference. All right, so you see that the same phenomenon also occurs for the molybdenum radiation. So we also know K alpha and K beta molybdenum radiation, and K beta is shorter than K alpha again. So the molybdenum radiation is overall having a lower wavelength than the copper radiation, and we can explain this by the fact that the molybdenum has more protons. Okay, and these additional protons, they exert a higher effective nuclear charge on the electrons in the K shell. So therefore, the 1s orbital in that K shell has actually a lower energy, and the energy differences between the K shell and the L shell, as well as the K shell and the M shell, is generally larger. Okay, so for our X-ray diffraction experiment, we want to use what is called monochromatic X-rays. So X-rays that only have one specific wavelength. So you can actually filter out the K beta radiation with a filter which is made of a metal with 1 proton less. Then this metal has actually the property that it has good absorption capabilities for that K beta radiation. If you want to even filter out the K alpha 2 from the K alpha 1 radiation, then you can do this by graphite single crystal using the principles of Bragg diffraction. And you can then use the reduced K alpha 1 radiation for your X-ray diffraction experiment. All right, so I think we can stop at this point.